right. Good morning, everyone. So let me also continue by sharing my screen on the other. Hold on a second. So let's share our screen. Okay.
Hocam en son bir tabloyu yarım bırakmıştık galiba. K1, K2 falan.
Yes, I'm gonna continue solving that. In fact, I was hoping that you would complete that, but still, I will still cover it actually. Okay, so it wasn't something really challenging. Okay, so let's say discrete time simulation continued, let's say. So this was our example, and we had actually obtained an equation, a computational equation, which was expressing the state variable h, the height of the tank. Remember, our example was the tank with free outflow. So this was a nonlinear system that we assumed a finite time interval, and we approximated the derivative operation by a finite difference along that interval. And that gave us, instead of a differential equation, okay, we obtained a difference equation. Okay, we obtained a difference equation. Remember that continuous time systems are characterized by differential equations, and correspondingly discrete time systems are characterized by difference equations. Okay, so here we have a difference between hk and hk minus 1. So we can express hk in terms of hk minus 1 plus this was our interval, the time interval. We can call this the sampling period, basically, minus the square root of hk minus 1. Remember that we have taken our parameters to result in very simple equation, essentially. All the coefficients, we have taken them in such a way that we had very simple coefficients for us. So so our table was something like this. We basically start with k0, and successively we try to compute the h value for successive k's. Okay, and I'm going to do this for a number of very small number of cases, and I would like to do this for two different cases. Okay, so let's say that in here the case is h0 is equal to 0, and in the second case h0 is equal to 2. Okay, so this starts from 0, this starts from 2. And I'm going to make the calculations for the first column, but I'm going to just fill in the second column, and you can verify that. Okay, so if h at 0 is equal to 0, let's calculate what h at time 1 will be. Obviously, we are using this equation over here, right? So that's going to be hk minus 1, which is 0, plus 0.2 minus, oh, by the way, there is a mistake here. Let me write this again. Okay, so this is 0.2 times square root h k minus 1. Okay, so there was a mistake there. So this is 0.2 minus 0.2 times hk minus 1, but hk minus 1 is still 0, so this is 0. So this calculation gives us 0.2. So that means at k is equal to 1, this hk rises up to 0.2. Okay, let's continue with this. At time 2, k is equal to 2. Again, the equation tells me that I need to start from hk minus 1. So that's going to be 0.2 plus 0.2 minus 0.2 times square root of 0.2. Okay, so that's going to give you, if you make the calculation, 0.31 is what we end up here. Okay, 0.31 here. H3, again 0.31, the previous value, plus 0.2 minus 0.2 times square root of 0.31, and that gives us 0.39. Okay, so you see that the value is increasing, but the change from time step to time step is actually decreasing, right? The difference between the values is gradually diminishing. Okay, H4 is equal to, in a similar way, okay, it gives us 0.46, and H5 gives us 0.52. 0.52. Okay, so this is 0.46 and 0.52 is how it goes. And if we do the same for the other initial condition, which where we start from 2, let's also kind of fill in those values. So this starts with 2, so it goes to 1.92, 1.84, 1.77, 1.70, 1.64. Okay, again the difference starts larger, and it gradually diminishes. So if I wanted to sketch this, okay,
Bu lineerde de böyle oluyor değil mi? Yani azala azala şey oluyor. Time step'ler arasındaki difference.
time step'ler arasındaki difference aynı. Ama fonksiyonun, yani h fonksiyonunun değerleri arasındaki fark giderek azalıyor. Yani bir nevi exponential bir davranış var. Önce hızlı değişiyor, sonra yavaş değişiyor. Let me sketch it, and then you guys continue asking your questions. Okay, so let's put our axes here. Okay, so if this is our h of k, and if this is essentially our k index, which corresponds to our time. Okay, so in fact, if you simulate this, okay, what you will end up with is something like this, right? So the first trace will start from 0 and will gradually approach 1. And if you start from 2, what's going to happen is that it's going to approach again 1, okay, in an exponential manner. Limit in both cases is h is equal to 1. So this, the tank, the height of the liquid in the tank, independent of where you start initially, if you have a constant input, the tank height will essentially approach a limiting value, which in this case is 1. It's going to approach 1. I also quickly kind of typed something in MATLAB. In fact, you can very easily simulate this in MATLAB yourself. I will put out the M file for you to play around with, but I would also urge you to implement it yourself. Difference equations, what is good about difference equations is that they are very suitable for computer implementation. A difference equation essentially is a recursive formula where you start from an initial value and you can successively compute all successive values. In fact, differential equation solvers, numerical differential equation solvers, are often based on some kind of a discrete time approximation, almost always. We have approximated the derivative by a finite difference. Often what is being done is that the integral operation is approximated by a finite difference calculation of the area. Both are possible because you can take the integral of both sides in the differential equation, and the left hand side becomes the function of interest. The right hand side becomes an integral formula. Okay, so what have we done? Well, we have derived a continuous time nonlinear model. Okay, let me summarize what we have done. So let's say notes. So yes, go ahead.
Hocam bu sistem causal değildi değil mi? Causal olması şart değil yani. Sonuçta bir input verilmeden tanktaki suyun bir yüksekliği olabilir yani başta diyor.
Bir sistemin, so what you are talking about is not causality or non-causality, okay? It's rather the presence of an initial condition. So the system, as we have written in our difference equation, this is a causal system. This difference equation at the top, this difference equation is a causal difference equation. Why? Because any value at time k of the state is actually expressed in terms of past values of the state and also the present value of the input. So this is a causal system. It's not attempting to use any future values in time. So this system is causal, but it has initial condition, at least in the second column.
Hocam şey diyecektim, h0'da eşittir 0 demişiz ya, mesela o denklemi sağlamıyor. O sıkıntı olmuyor mu? Initial condition olduğu için ona bir exception mı şey yapıyoruz yani?
Denklemi sağlamamaktan kastınız nedir?
Hani k eşittir 0 verdiğimizde mesela
Evet.
h0 eşittir 0.2 çıkıyor ama ilk sütunda h0 eşittir 0 diye
Ama h0'ı hiçbir şey cinsinden ifade edemezsiniz. H0 bir given olmuş oluyor. Sadece h at time 1 hesaplanabilir durumda şu anda.
K eşittir birden hesaplamaya başlıyoruz. Yani.
Tabii ki, çünkü verdiğimiz denklem causal denklem de sol tarafta k var, sağ tarafta hiçbir şekilde k yok. Sadece k eksi 1 var. Yani h at k'yı hesaplayabilmek için sadece k eksi 1. ana kadar ki, hatta burada recursive bir formül olduğu için sadece k eksi 1. andaki state'i kullanıyorum. Tabii ki bir de bu andaki, yani k anındaki input'u kullanıyorum.
Anladım hocam, teşekkür ederim.
Onu 1 olarak aldık çünkü flow değerini sabit olarak aldık, 1 olarak aldık. Ama inflow değeri zamanla değişiyor olsaydı o zaman sağ tarafta u of k diye bir şey olacaktı.
Input da zamana göre değişiyor olacaktı. O da etkili olacaktı. Ayrı
Tabii ki. O zaman şey olacaktı. Ben state'in bu andaki değerini hesaplayabilmek için input'un da bu andaki değerini kullanabilecektim. O zaman denklemin sağ tarafında input'un da bir fonksiyonu olacaktı. Linear veya nonlinear.
Anladım. Teşekkürler.
Is there any other questions?
Ben de küçük bir şey soracaktım hocam.
İsim?
Özgür.
Buyurun.
Bu uzun süre sonunda, yani steady state'te ulaştığı ya da yaklaştığı değerin input'la, yani Q'in değeriyle aynı çıkması tesadüfi bir sonuç mu? Yoksa biz initial condition'ların hani steady state'le etkisinin olmadığını circuit'ta falan görmüştük. Tamamen input'a bağlı bir sonuç çıkıyordu. Burada da benzer bir durum mu var?
Arkadaşlar 302'yi hatırlayın. Bir sistemin referans input'una verdiğiniz değerin output'un limit değeriyle aynı olması ne anlama geliyor?
Zero ESS, yani
Aynen öyle. Bütün sistemlerin zero ESS'i mi vardır?
Hayır. Ama yani input'la yani initial condition'dan bağımsız olarak input'un belli bir farkı olarak çıkacak değil mi? Bu steady state olduğu için.
Aynen öyle. Sonuçta ama şöyle bir requirement her zaman yok bütün sistemler için. Output'un steady state değeri input'a eşittir diye bir şey yok.
Tamam.
Input'tan farklı bir yere converge edebilir. Bu durumda biz eğer input'u referans değeri olarak algılıyorsak ki o genelde feedback sistemlerde bu şekilde algılanıyor. Yani hani feedback sistemin input'una biz referans adını verdiğimiz için output eğer başka bir yere converge ederse biz sistemin steady state hatası vardır diyoruz.
Anladım. Yani biz input'u mesela atıyorum hafif böyle sinusoidal gibi bir osilasyon verseydik output'ta da onun olmasını bekleyeceğiz. Belki biraz shift, belki biraz amplitude farklı ama yine osilasyon bekleyecek.
Bilmiyorum nasıl davranacağını. O sistemin dinamiğine bağlı. Ama bu sistem tabii ki belli bir time constant'la bir yere converge ediyor. Dolayısıyla değişken bir input verdiğinizde de gene o time constant'a bağlı olarak o input'u takip etmeye çalışacak bir şekilde. Bu arada şunu söylemek lazım. Sistemler genel olarak bir input'u ve output'u olan bir sistemde output'un illa input'a converge etmesi çok anlamsız bir şey olabilir. Mesela sistemin input'u voltajdır, output'u açıdır. Şimdi elmalarla armutlar varken açının voltaja converge etmesi diye bir şey bekleyebilir misiniz? Bekleyemezsiniz yani. Output bir açı, input ise bir voltaj mesela. Veya output bir velocity, mesela bir motoru düşünün. Değil mi? Bir DC motor, tipik armature control DC motor, biliyorsunuz belli bir yere kendi kendine converge eden bir sistem. Yani sabit bir voltaj uyguladığınızda output shaft hızı, dönme hızı belli bir değere converge edecek. Doğru mu? Ama bir tanesi radians per second, öteki voltaj, volts. Dolayısıyla hani aynı değer kavramı fiziksel anlam olarak bile tanımlı değil. Okay? So let me summarize what we have done. Initially, we have derived a continuous time, nonlinear differential equation model of the system. The system was tank with free outflow. As a second step, what we have done, we have discretized. Remember that discretization may be defined in different domains. We have discretized in time. That means the system has become discrete time. We haven't discretized the values themselves. If you discretize both the time and the voltage values or the physical variable values, we usually call the system digital, in the sense that you also represent the numbers with finite precision. Okay, to obtain a nonlinear difference equation. So the model has become a difference equation rather than a differential equation. And then we have simulated. This is called a simulation, a numerical run of the system model. The system simulated is what I meant. Simulated the system numerically to compute the state. Okay, so in terms of the time interval that we have considered, it was 0.2 seconds, okay, in our case. What do you think will be the accuracy of this simulation in terms of this time interval selection?
Yani selection arttıkça convergence ya settling daha iyi görebiliriz. Bence. Çok büyük değil.
Who's speaking?
Ege hocam ben.
Okay, not very clear what you are saying.
Oscillation falan varsa mesela, bu case'te yoktu ama diyelim ki varsa falan diye dedim.
Now, tell me what it means. What do I mean by accuracy of the simulation?
Ne kadar yaklaştığı falan.
Neye ne kadar yaklaştı? What is the reference that I'm talking about?
Limit değerini işte o bizim gösterdiğimiz
Careful. Somebody else maybe?
Continuous time adına ne kadar yaklaştı?
Who is speaking again?
Özgür hocam.
Okay. So what you are saying is how much the behavior approaches the continuous time behavior. Is that correct?
Yeah.
Okay, that's correct, right? So when we talk about the accuracy of a discrete time approximation, what we mean is how this behavior actually represents the behavior of the continuous time system. Now, can you tell me the answer to my question? What happens in terms of accuracy, of this accuracy, as a function of this interval time or the sampling time, delta t?
Delta t arttıkça accuracy düşüyor.
Correct, right? So as we make this interval smaller and smaller, remember the derivative is defined as a limit. So the derivative is the limit of the difference divided by the interval as the interval goes to zero, correct? So as we make the interval smaller and smaller, we have a better and better approximation to the derivative operation. And that means the accuracy of the discretized version improves in terms of it approaching the continuous time equation. Okay? So let's also put this down. The accuracy of the discrete time approximation let's say how much its behavior approaches the behavior of the continuous time version, the accuracy of the discrete time approximation improves as delta t goes to zero. Okay, the smaller the time interval, the better the approximation. Okay, now let me ask you another question. What's the main difficulty if I wanted to consider the continuous time version, and suppose that I wanted to control this system, and you come from feedback systems course 302, and you want to design a controller for this system? What's the difficulty?
Bir daha söyleyebilir misiniz?
Kaçtı soru. You come from with the knowledge of the methods and techniques in 302, right? So we have seen another system here, and we have derived the differential equation model, and you want to design a controller for it. What's the difficulty? Can you design a controller for this system? If not, why?
In feedback systems, we were using transfer functions and block diagrams, but it was only true for linear systems, but the system is not linear, so I don't think we can design I mean, if we linearize the system somehow, we can design a controller, but not like this.
Okay, that's a good answer, right? So the main difficulty here is that this system is nonlinear. Okay, because the system is nonlinear, we don't have yet any method or technique that can be used to design a controller for a nonlinear system. Okay, so that's going to bring us to our next topic, which is essentially an introduction to the concept of the equilibrium point, the operating point, and the concept of linearization. That means finding a linear approximation around an operating point where you can derive a linear approximation to this nonlinear system. Okay, so before we move on to that area, any questions related with what we have done so far?
Benim bir sorum vardı hocam.
Sure, that's when you ask the question.
Hocam biz continuous time differential equation'ı discrete time'e geçirirken orada türevin tanımını kullandık sanırım.
Yes.
Ama türevin tanımında yukarıdaki terimlerin içleri arasındaki farkı aşağıya yazıyorduk biz direkt. O yüzden aşağıya delta t yerine 1 yazmamız gerekmez miydi? Yani hk eksi 1 bölü aşağı 1 yazmamız gerekmez mi?
Arkadaşlar, d over dt h of t definition nedir? Limit delta t goes to zero,
Evet.
h t plus, sorry, let me use continuous time notation, t plus delta t minus h t divided by delta t. Definition bu değil mi?
Evet. Aynen.
Tamam. Ne sıkıntı yaşadınız burada? Biz sadece şöyle bir şey yaptık. Şimdi bu definition non-causal
Evet. Non-causal olan.
non-causal derivatif işlemi causal bir işlem değil. Çünkü ileriki zamanı kullanıyorsunuz. Halbuki ileriki zamandaki değere sahip değiliz.
Anladım.
Dolayısıyla
Causal
bu
olana geçti.
şu şekilde approximate edilebilir. Eğer delta t yeterince küçükse, ki limit aldığımız için küçük varsayıyoruz, bir causal approximation'ı da şu olabilir. T minus delta t divided by delta t.
Hocam bunu discrete'e geçirirken kısmını sanırım.
Discrete'e geçirirken ki yaptığımız şey şu. Sonuçta şöyle diyoruz. T equals k times delta t olsun diyoruz.
Anladım. Tamam hocam anladım ben.
Ondan sonra da delta t'yi atıyoruz. Çünkü delta t her yerde sabit olduğu için artık yukarıda h of k times delta t demek yerine artık h of k diyoruz. Ve anladığımız şey delta t aralıklarla, yani sonuçta düşünürseniz burası gerçek continuous time ise ben burada artık k equals 1 demek, aslında ben delta t'deyim demek. Özür dilerim. Evet, delta t'de. K equals 2 demek şurada. 2 çarpı delta t'deyim demek. Bu şekilde gidiyor.
Tamam hocam anladım ben şu an.
Okay.
Tamam.
Any other questions?
Yes, I have a question. I am Atakan.
Go ahead.
Okay, in this situation, the discrete simulation and the continuous, the case continuous case seem to be converging the same value. But could we imagine a scenario where our delta t is not good enough such that we won't be able to converge to the continuous case?
That's perfectly the case. In fact, hopefully in EE402, okay, you will dive into the intricate details of how much delta t should be small, what happens if it's not small enough, what kind of behavioral changes there are as delta t becomes larger, and so on. Obviously, delta t becomes a factor in how close the approximation follows the continuous time. And if delta t becomes larger and larger, it is perfectly correct what you have said, is that the behavior will start to go farther and farther away from the behavior of the continuous time.
Could we have an oracle to tell us how to fix that simulation result? Maybe we could not have shortened our delta t because we don't have enough computation, but by some oracle, or I don't know, some decision making.
Well, we don't have an oracle, and the definition of an oracle is somebody who predicts the future, in fact, who can foresee the future, which is a fundamentally non-causal premise, right? So, but there are algorithms called predictors, which, given other information, they can actually make predictions about the future based on entirely data from the past. And we will see some versions of predictors, but these are not for, yes, they may give you a better behavior under larger delta t's. In fact, even forget about that. Yani şöyle, Türkçe söyleyeyim bunu. Sonuçta şöyle, biz çok crude bir approximation yaptık. Derivative olabilecek en uyduruk approximation'ı kullandık şu anda. Finite difference approximation. Her şeyden önce daha iyi approximation'lar var. Yani daha büyük delta t'ler için daha iyi derivativi represent edebilecek approximation'lar var ki bunları 402'de görmeye başlamış olmanız lazım. 402 alanlarınız için söylüyorum. 402 alıyor musunuz?
Evet, alıyorum.
Söylediğim bir şey ifade ediyor mu?
Yok, daha o yeni, daha kompleks bir derivatif yöntemini falan görmedik ama yavaş yavaş gideceğiz gibi geliyor, hissediyorum.
Tamam. Yani sonuçta 402, yani discrete time kontrolün zaten amacı temelde farklı delta t'ler için discrete time approximation'ın nasıl davrandığını da anlamak. Çünkü bir sistemi siz bir computer'da implement etmeye çalıştığınız zaman, mesela bir kontrol sistemini diyelim ki kontrol sistemini siz continuous time'da derive ettiniz. Root locus kullandınız, işte buldunuz bir şeyler, bir K buldunuz, dolayısıyla proportional controller buldunuz ve bunu discrete time'da implement edeceksiniz. Bilgisayarda finite zaman aralıklarında hesap yaparak bunu kullanacaksınız. Bu implementation'ın continuous time'da derive ettiğiniz davranışa ne zaman yaklaşıp ne zaman uzaklaşacağını bilmeniz lazım. Doğru mu? Bunlar 402'nin konuları. Yani continuous time bir sistemi discrete time'da nasıl en iyi şekilde modelleyebilirsiniz? Sonuçta delta t biliyorsunuz bir resource problemi. Yani delta t'yi ne kadar küçültürseniz birim zamanda o kadar çok hesap yapmak zorundasınız. Mesela biz delta t'ye 0.2 dedik. Bu şey anlamına gelir. Saniyenin 5'te birinde bir hesap yapmak zorundayız biz. Yeni bir sample hesaplamak zorundayız. Ama ben 0.001 deseydim delta t'ye, o zaman her saniyede 1000 kere hesap yapmak zorunda kalacaktım. Bu da sizin bilgisayar resource'larınızla ilgili bir şey temelde. Is there any other questions? Okay, so let me close this and open up a new page. I'm going to call this, where is my page? Okay, here we go. That's interesting. Okay. So EE407. Now let's call this big 5. So I'm going to give it a title here. Okay. So we will discuss equilibrium points. Equilibrium points. We will discuss operating points. Delta variables, the so-called delta variables, and the concept called linearization. Hopefully, if we are together next term, we will have a more formal treatment of this in state space as well. Okay, but for the time being, we will talk about it in a single input, single output scenario here. Okay, so let's assume that we actually have decided to operate around what we can call a nominal value of the input. Okay, let's assume that we operate around a nominal inflow rate. We still consider the same example. Consider our previous example. That means the tank with free outflow. And we assume that we operate around the nominal inflow rate. Okay, inflow rate. What does this nominal mean? Nominal, we can say it's a usual, practical, desired. Okay, desired. So in a plant, for example, you might want to actually this, let's say the process, the chemical process would have a nominal material processing rate, so that the material inflow will be at a certain rate and the outflow will be at a certain rate, and things will be kind of in equilibrium. Okay, so we call this a nominal inflow rate. Okay, now the question here is, can we also find a corresponding value for h of t? That means if I'm operating with a nominal inflow, is there also basically a nominal fluid height? Okay, and let's call this okay, nominal is kind of we use it in a way equivalent to operating. Okay, so nominal inflow rate means operating inflow rate. Okay, so let's say that h of t, such a value exists, and this is constant. We call it HOP, such that the system is in equilibrium. What is equilibrium? Equilibrium means no, if you have no change in Q in of t, so if your inflow rate is constant, means no change in h of t. So equilibrium is a mathematical definition where if you have a constant input, you maintain a constant state. Okay? So that is the definition of equilibrium. So what is the mathematical definition of equilibrium? It means that you have no change. Okay? Equilibrium means that you have we had a in front, but it is really dh of t over dt is what is important. It has to be equal to 0. Okay, no change in the state is the definition of the equilibrium. Okay, this is called equilibrium. Sometimes it's called an equilibrium point, but the point keyword is kind of misleading, as we will see in a minute, or operating point. Now let's see what happens in our case with this definition of the equilibrium. So remember that our differential equation was something like this. So we had a dh of t over dt plus a square root of 2g square root of h of t is equal to q in of t. So we had an input. This was our input, and this was our state. Okay, the height of the liquid in the tank. So now we are imposing equilibrium condition. So this becomes 0. So what you end up with is an equation in terms of the state itself, h of t, and q in of t. Now, because I'm imposing equilibrium, I now have constant h of t. So h of t becomes hop, and q in of t becomes qop. Let's say q in op. So this gives us, I have, if I write this, I have a times square root of 2g square root of hop is equal to q in op. And if I take the square of both sides, a square 2g, I have hop, and that is equal to q in op squared. That means I can actually calculate also HOP in terms of Q in OP, and that's going to become simply Q in OP squared divided by A squared 2G. What is important here is that you can express Q in OP in terms of HOP, and you can express HOP in terms of Q in OP. Okay, so note both Q in OP, the operating value of the input, and the state can be expressed in terms of each other. Okay. So what we mean, or what's the definition, is that at this point, at Q in of t equals Q in OP, a constant, and H of t being equal to HOP, we have dH of t over dt is equal to 0, and we say system is at equilibrium. We call HOP as the equilibrium state. And we call Q in OP as the equilibrium input. Okay. Now, in previous years, we had an experiment in 302 where you have basically an arm moving up and down around a pivot point, and we had a propeller mounted at the end of this arm. So as you give a voltage to the motor driving the propeller, this arm was lifting up and down. Okay, this is a nonlinear system because gravity is always pointing downwards, and as the angle changes, obviously gravity is decomposed in terms of the sine and cosine of the angle. Therefore, you have a nonlinearity in the system. So if you want to talk about an equilibrium state, you would drive the motor. If you drive the motor harder, you will arrive at basically a point with a larger angle. If you drive the motor with a slower speed, you will arrive at an equilibrium somewhere over here. So you can actually play around with a constant input so that the system will stabilize around a certain angle. So the equilibrium input is how much voltage you give the motor, and equilibrium state is what's going to be the resulting angle. Okay, this is different from the concept of stability. For example, you can adjust the motor and you are at a certain angle, but if there is no controller at all, and if you keep the motor voltage constant and you bump, this arm, it's just gonna fly around at some other place. So it's gonna become unstable. Okay, so stability is something entirely different from equilibrium. An equilibrium point might be stable or unstable. Let me give you another example and then we will have a break. Think about the pendulum. Okay, now the pendulum is a system without any input. So there is gravity involved. Okay, so think about it. Here there are two equilibrium points. One is downwards and one is upwards. Okay, in both cases, as long as the angle is actually equal to either 0 or theta, 0 or pi, the derivative of the angle will be equal to 0. But the bottom equilibrium point is a stable equilibrium point. Why? Because if you disturb it, it's going to come back. It's going to want to come back to the same point. Therefore, a stable equilibrium point. And if you think about the top angle, even if you disturb the pendulum by an infinitesimal amount, it's going to want to just go away from that equilibrium point. And therefore, this particular equilibrium point is called an unstable equilibrium point. Okay, so that's just a side note. Let's give a break and then we will come back and I will answer your questions. Okay, it's 35 past 10 and we have 10 minutes break. Görüşürüz arkadaşlar.